When it says applications of trigonometry, barely. I mean, really, barely is what we're talking about here. So, what we have to do is have a good understanding of vectors. And that's because hopefully most of you will be going into some type of engineering field or science field. And whenever you do, you're always talking about vectors. Absolutely always. So, Chapter 6, Applications of Trig, says young salmon migrate from the freshwater they're born into saltwater and live in the ocean for several years. When it's time to spawn, the salmon return from the ocean to the river's mouth, where they follow the organic odors of their home stream to guide them upstream, so literally by scent. Researchers believe the fish use currents, salinity, which is the salt in the water, temperature, and the magnetic field of the earth to guide them. Some fish swim as far as 3,500 miles upstream for spawning, and we've got some problems later on. I don't think that we get any of those spawning salmon things. We talk a little bit about it as far as currents of a river, but that'll be a little later. So what to expect? Just 6.1, half of 6.2, a little bit. This chapter reminds us of the uses for vectors in a plane and some basic operations with vectors. Vectors are used to represent many quantities such as force and velocity. No doubt you've used them or will use them in your science classes in the future. Vector methods are used extensively in physics, engineering, and applied mathematics. One thing that drives me nuts about this book is they use this symbol for vectors. That's not the symbol for vectors. That's the symbol for lines that you had way back in geometry. The true symbol for vector AB only has half of an arrow on it. So the book claims that there are other books that do this too. I have yet to see one. If you want people to know the difference between vectors and lines, we use different symbolization for that. So please use the correct symbolism for vectors here, which would be half of the arrow, not the whole thing. Now, we're going to talk about two-dimensional vectors. So they have an x component and a y component. Vector operations, unit vectors, direction angles, applications of vectors. Direction angles is where we use a little bit of cosine, sine, tangent in there. So that'll be our little bit of trig. Dot product, that'll be brand new to you. Angle between, oh wait a minute though, some of you might have dealt with dot products and vectors in your science classes. So that might not be brand new to you. Angle between vectors, again, a little trig there to find the angle. We are actually not going to do projecting one vector onto another. We will not cover that. So, we will do a little bit with work, although we did that in 9th grade science class. Do you remember that? Force and work and all that good stuff? Yeah. So, just a little reminder about those things. So, 6.1 is about vectors in the plane. We want to be able to apply the arithmetic of vectors. We want to be able to use the head minus tail rule, the HMT rule, find magnitude, look at vector addition and scalar multiplication, which are very basic. We want to find a unit vector, which has just a little bit of, well, it's mostly once we learn all the symbolism and what it's for, we'll be totally fine. Resolve a vector, probably not today. We'll see how this goes. We've got quite a lot to get through because Monday, most of the classes are going to be making rounds at the elementary schools because seniors go to do the senior lock on Monday. So I'm going to try to get through everything I can, but then, of course, make a video on Monday for any of you that are gone because we definitely won't get to the starred one, using vectors to solve real-world problems. So I'll have to make sure that I really detail everything out for you on Monday. Two numbers are all that it takes to represent both magnitude of an object's velocity and its direction. Most we simply look at ordered pairs of real numbers in a new way. And what we do is use this notation. It kind of looks like a less than symbol and an ordered pair with another greater than symbol on the other side. But that's called the component form for a vector. So what it's doing is it's showing us the x component and the y component. So that represents a vector. Now, these represent vectors that have an initial point at the origin. That's really a big deal right there. So what it's doing is it's saying this vector is going to start at the origin when we see the component form notation, and it's going to go to whatever A and B are, where that ordered pair is. And like I said, it's important that we know that component form means. These are going to start at 0, 0. That's their initial point. So down here we've got a little drawing, and we see the origin right here, and we see this point AB, and somebody says this vector is what I need to represent what's going on. So what they do is they just start with the initial point, one that doesn't have the arrow at the origin, and then put the arrow at the terminal point where it ends. And that makes this a component form vector of A and B. So the point represents the ordered pair AB right here, but if we make it a vector, then we change that notation and put it into that component form notation. So what do we do with all this? Well, this is definitely two-dimensional. We have an X for the horizontal and we have a Y for the vertical. An ordered pair of real numbers denoted in that component form. The numbers A and B are the components of the vector. This is how far we go right and left. This is how far we go up and down. The standard representation of the vector AB is the arrow from the origin to AB. So that's the reason that with component form, they don't say, you start at this point and here's where you end. We assume that it started at the origin. The magnitude of B is the length of the arrow. That's huge, by the way. Magnitude equals length. We don't need a new formula for that. That's distance formula. I already know how to do that. So if you're finding the magnitude, you're using the distance formula to figure out how long is this line. And like it says, the magnitude of B is the length of the arrow, and the direction of B is the direction that the arrow is going. Where is this going? The vector, zero vector for the origin, is 0, 0. And it is called the zero vector. It doesn't have length, it doesn't have direction. Basically, it's just a point. But it's because we have to have that for the definitions to work, 0 is called the zero vector. It is often convenient to represent vectors with arrows that begin at points other than the origin. And the important thing to remember is that any two arrows with the same length and pointing in the same direction, those represent the same vector. Now, they're going to use two different pieces of language here to talk about two vectors that are the same but in different positions. So when we look at these vectors, we can kind of eyeball it and say, hey, that looks about the same length as this one, and yeah, they're parallel. So those are equivalent vectors, but we wouldn't want to do that. We want to show the math. So the math would be, if I kind of think along the lines of how far has the x changed and how far has the y changed or slope, I can get an idea whether or not this little 3, 4 is going to be helpful over here. So I think, well, -1 minus a -4, to see the difference in those two x's, that would give me a 3. And actually, just write that component 1. And if I take 6 minus 2, that'll give me 4. Well, this one over here, the terminal point is at 3, 4, and we're starting at the origin, so pretty obviously 3 minus 0 is 3, and 4 minus 0 is 4. Those are two equivalent vectors. They're not located in the same spot, but they're equivalent. So the arrows for RS and OP, and this is the point they're trying to make. Arrows don't mean the same thing here that they did in geometry. This is just the way that we represent vectors. We're actually saying that there's direction here. It's going up. So that's what the arrow is doing. It's not saying it goes forever, like grades when you're in geometry. It doesn't. It's just showing us it's traveling this way. Here's the initial, and here's the final. So the arrows for RS vectors, RS and OP, and again, that drives me nuts. Both represent the vector in component form 3, 4, as would any arrow with the same length pointing in the same direction. Those are called equivalent, and because you're going to need this for your homework, and parallel. And obviously they're parallel. Now, if you take a look at that, we saw the slope is the same, and the slope is the same. Then you'd have parallel lines. In this case, we're talking parallel vectors. So when we get those exact same component forms, they're not just equivalent, but they're parallel. Now that's important because in the homework they're going to give you a vector and they're going to say, give us one that would be parallel to this. All you have to do is put the slope the same. That's all you have to do. So down here, is an arrow a vector? No. is a representation of what we do. So an arrow represents a vector because we want to see direction, and we also want to know where is that terminal point and that initial point. So each vector can be represented by an infinite number of equivalent arrows. It's just where you want to draw it on the coordinate plane. Still, it says it's hard to avoid referring to the vector PQ without that notation in practice. And that's why most books will not put that line on the top. Most books, especially anything you take at college, there's a class usually called Vectors and Matrices, will have that notation instead of the arrow. So in practice, we're going to do that. We're going to call this vector PQ, but we know it doesn't go on forever. We know that arrow is for direction. So the other way we could refer to vectors is we could just say that equals vector D. Just give it a letter, a lowercase letter to stand for the vector. And usually books will put those in bold, so it doesn't just look like any other variable that we're dealing with. You have a bold D, and that'll show you that that's going to happen, and that'll be a vector. So now, the head minus tail rule is what I was just doing earlier, just doing a little subtraction. So if an arrow has an initial point at x sub 1, y sub 1, and a terminal point at x sub 2, y sub 2, we want to find out what's the change in the x's, what's the change in the y's. Because vectors always have a horizontal component and a vertical component. And if we're going to find that, we have to do subtraction. So we're going to take the terminal point. Notice this is really important. I was thinking while I was doing the homework, they didn't spend a lot of time explaining this. You have to take terminal point minus initial point. And if it's in component form, remember that we're talking about something that starts at 0, 0. Starts at that 0 component form, 0 vector. So terminal minus initial. So how are you going to know from a drawing? The terminal one has the arrow. So that's the one you use first, and you subtract the other one. The one that's just a dot or the end because it has the arrow on it. So that doesn't sound too bad. That's not very bad math. Subtraction, I think we can do that. Show that the arrow from R to S is equivalent to the arrow from P to Q. Okay, not a problem. RS. All right, so for RS, I'm going to need to take arrow minus initial. So terminal minus initial. So -1 minus a -4. And then terminal minus initial for the y's, so 6 minus 2. A -1 minus a -4 is -1 plus 4, which is 3. And 6 minus 2 is 4. So if these are going to be, like it says, equivalent, again, in other words, these are parallel, we better get the exact same thing for vector PQ. Well, that one would be 5 minus 2, terminal minus initial, 3 minus a -1. Oops, too many parentheses there. Well, 5 minus 2 is 3, and 3 minus a -1 is 4. And it said show, and we did show. They are equivalent. And go a little further, parallel. Because they are. They have the same component form, they are. So this is why this is called the head minus tail rule. They call the one with the arrow the head, and they call the one without the tail. So head minus tail. It's not bad. Well, they got to mess with us somehow here. So it says, see how well you can direct arrows in a plane using vector information and what we know about the head minus tail rule. An arrow has initial point at 2, 3 and terminal point at 7, 5. What vector does it represent? So let's give the component form. What would you put for the x? Yep, 7 minus 2 is 5. How about the y? 2. Well, I hope they're not all like that. Kind of a waste of our time. They're not. The next one says, initial point was at 3, 5. this is what the component vector was. What was the terminal point? So they took some x and they subtracted 30, and they got a negative 30. And they took some y and they subtracted a 5, and they got 6. Now, do you have to do that formula about it? If you're looking at this saying, well, can't I just work backwards? Yeah, then do that, you know. Think backwards to, all right, I've got something minus 3 has to be negative 3. And do it that way. Oops, this is a point. What is the terminal point? Almost wrote that as a vector. And you can think backwards, something minus 5 was 6. What would that something have to be? Something minus 6 is 5. Something minus 6 is 5. Yeah. There we go. Alrighty, let's go on to 3. If P is the point for negative 3, and PQ represents 2, negative 4, find Q. Well, the first thing to think of is P the initial point or is it the terminal point? Which is it? Initial. So we're doing the same thing we were doing before. We're saying it was something minus 4 equals 2. Something minus a negative 3 gave you a negative 4. So you could set it up algebraically. What minus 4 gives you 2? What minus a negative 3 gives you negative 4? Yeah, that one's a little bit easier to do algebraically because it's like there's so many negatives to keep track of here. And work backwards for. This one says if Q is the point for negative 3, and vector PQ represents the component form 2, negative 4, find P. So is the 4, 3 initial or terminal? Oh, so this time we're going to do this. So 4 minus x had to come out to 2, and negative 3 minus y had to come out to negative 4. Or you could think backwards. 4 minus something is 2. That something is 2. Negative 3 minus something was negative 4. What's the something? Add 3. Divided by negative 1. Should be more people telling me what this is. 1 minus a negative 3. There it is. Alrighty. Magnitude. Magnitude. Magnitude equals length. Magnitude equals length. Oh, we can find that by the distance formula. So the magnitude or norm. Not many books are going to use norm. Most books will talk about it in magnitude. The magnitude or norm of vector B is also called the absolute value of B. Now that makes it confusing. I'm going to refer to it as the magnitude of B. And it says is usually denoted by, and I'm going to tell you, that's not the way you're going to see it in college. It's double bars. That's what we do with vectors and matrices at college. We use the double bars so that it's not, people aren't getting distracted by the fact that, hey, that looks like absolute value. Because it's not absolute value. It's magnitude. So the double lines. Non-negative real number, because it's distance, and it's not a vector. It's, hey, it's this long. That's what it is. That's the magnitude in length. So we see what should look very familiar, which is the distance formula right here. If you want to know the length, you find the difference between the x's, square it. Find the difference between the y's, square it. Add them together and take the square root. That's the distance formula. But now we're doing this, hey, this is equal to the magnitude of the vector. So that's what it is. Magnitude of the vector is length. Now, if it's in component form, remember, the initial point is at 0, 0. So think of putting zeros right here and right here. Well, we're not going to x squared and y squared, or in this case, I used a and b squared because we had our component form as b. So a little easier when it's in component form. So up to you whether or not you want to put it in component form first and then put it in the formula, or just use the distance formula, either way. So this one says we want to find the magnitude of the vector b that's represented by our vector pq here, where p is -3, 4, and q is at -5, 2. Well, there's my terminal point. So I think I'm not at 0, 0 for my initial point, and I just want to know and find the magnitude of vector b. That distance. All right. Well, -5 minus a -3 squared plus 2 minus 4 squared. -5 minus a -3 is -5 plus 3, which would be -2 squared, and so would 2 minus 4. Well, that's 4 and 4. When you add 4 and 4, you get 8. So the magnitude of b equals the square root of 8. But we know we can simplify that. What does the square root of 8 simplify to? 2 square roots of 2. Exactly. Now, sometimes the book will leave them in radical answers, and a lot of times they're going to put it in decimal form. It just depends on what we need it for. So that is the magnitude of that vector. It's just the distance. So, here, I know there were some problems in the homework that got a little weird. Nope, that's example 4. So we'll talk about the weirdness in example 4. All right, this one. Vector operations. Not the toughest thing we're ever going to do. The algebra of vectors, pardon me, sometimes involves working with vectors and numbers at the same time. Those numbers are referred to as scalars. So we want an equivalent and parallel vector. But we need longer. We need the magnitude. All we do is multiply it by a scalar. That's all we do. So the two most basic operations that we use with algebra with vectors are going to be vector addition, very basic, add the x's, then add the y's, and scalar multiplication, just multiply everything by a scalar. So scalars, again, is just a number. You know, that's all it is. You can think about trying to blow up a picture that you like. You know, you're going to multiply that by a number in order to get the Photoshop to make it bigger or smaller, depending on what you want. Vector addition and scalar multiplication. Let U be the component form of U sub 1, U sub 2, and V be the component form V sub 1, V sub 2. And those are vectors. And let K be a real number. K. Sum or resultant of those two vectors is whatever you get when you add them together, U's with U's and V with V's, for addition. But the product of K and a vector, all you do is multiply them by K. You only have two numbers, so we'll multiply two numbers by K. Logan, either you really like vectors or you're watching something you shouldn't be right now, so please close up. In the tail to head representation, the standard representation of U points from the origin. Again, origin to U sub 1, U sub 2. The arrow from U sub 1, U sub 2 to that new terminal point represents. We've done that with that head minus tail rule already today using subtraction. The arrow from the origin, U sub 1 plus V sub 1, U sub 2 plus V sub 2, then represents U plus V. Here's what we do. If we want to add two vectors together, imagine this red one isn't here. What we do is we make sure that we match up the head to the tail of the other vector. So wherever this V vector is, we'd say, well, this is U. Slide that V vector so that the head and the tail of these two match. And when I do that, from the initial point to the final point, that's going to be where my U plus V vector is going to be at. So over here they show us that. If we had a U plus a V vector, two things we could do. We could take the V vector and slide it up and put it right there to make a parallel slide it over so that the tail and the head match. Either way, the diagonal of that parallelogram is where our vector is going to be. So that helps us visualize what we're going to get when we add our two vectors together. So down here it says, in the parallelogram representation, which is just a really basic representation that all books use to talk about vector addition, the standard representations of U and V determine a parallelogram, and the diagonal is actually the result, the sum, that U plus V that we get. But it's much more basic than that, especially if it's given to us in component form. All we're going to do is add. All we're going to do. So the product KU of the scalar K and the vector U can be represented by a stretch or a shrink of U by a factor of K. So if K is a number bigger than 1, you're going to stretch it up. And if K is a fraction between 0 and 1, you're going to shrink it. That's what we use those for. So if we want something to have the same direction, but a different magnitude, then that's what we use this for. K. So notice that for everything that we have here, this would be in the same direction if we multiplied by 2. But it is possible to get your vectors to go in opposite directions. I just want to positive to negative. I can use a negative K value, and that will reverse that direction. So down here, they're going to give us a little math to do with these vectors. When I say little, I really mean little. Because all we're going to do for U plus V is add the horizontal components and the vertical components. That's all we do. So we look at this and say, hey, here's an X and here's an X. Let's add those together. Here's a Y and here's a Y. Let's add those together. That's vector addition. You know, it works, so why not use it? It works. Then B has us use a scalar on a vector. So 3 times vector negative 1, 3 in component form. Again, I feel kind of silly having to go over this. All we're going to do is multiply both numbers by 3. That's a scalar. It'll be in the same direction. It's just going to have a bigger magnitude. And the last one, yeah, well, we got to do a little algebra type of thing here. We're going to take 2 times U, so 2 times our negative 1, 3 component form vector, plus negative 1 times our component form vector V, 4, 7. And like I said, just think of this as algebra. And we'll do just fine. Follow the order of operations. So do the multiplication first. And then do your addition. So far, if we just stop right now with vectors, 4, 3, 2, 1, 0 means, how do you feel about that? Yeah, too bad we can't just stop. Just so far, just everything with vectors we've done so far. Yeah. So vectors are not scary. So again, that word trig on the front, I don't want anybody to start getting all weird about that. It's not that much trig, okay? Here we see the parallelogram thing again, just a representation of what's going on. If you had U plus V and you match those up head to tail, and that would be your diagonal for a parallelogram, because if we took this vector and tried to put it here, we'd end up with a little parallelogram, and that would be the diagonal. So we can make that happen. Now, that's what vector addition does. Scalars, you're either stretching or you're shrinking. That's what we're using it for. So it's traveling in the same direction, but it has different magnitude. And I keep saying that because they're going to ask you to do that in the homework. And for a second, you're going to go, I know this was really easy. But how do you do that? Same direction, different magnitude. It's just a scalar. That's all you do. You multiply by a scalar. So down here, a word about vector notation. There are several different ways to write vector notation. And this component form is by far the easiest. So we want to be able to do that. So both notations, AB and AI plus BJ, are used for vector notation. The easiest one to work with is always component form. So if you're thinking, well, what am I supposed to do with this so that I can make it look like that so I could use it? Well, I stands for the vector that has component form 1, 0. stands for the vector that has component form 0, 1. So really, all we need to know is A and B are going to be the x-coordinate and the y-coordinate. So when we see this, we're just going to change it to component form so we can do the math. We're not going to spend a lot of time worrying about the i's and the j's and the k's and all that good stuff. And it definitely could be used in 3 dimensions as well. So we could have a component form ABC, and we could see that as AI plus BJ plus CK. Now they're going to throw a couple of those at you in the homework. Don't let it throw you. Remember, all you have to do is grab whatever's in front of the I, the J, and the K, and that will be your component form. All right. Oh, and it does say here, scientists stick to our component form notation for dimensions higher than 3, because usually if they're going 3 or 4 dimensions and using time as a dimension, they're going to do math with it. And so component form is much easier to use when you're doing that. All right. Now, what we want to do next is what's called a unit vector. And what a unit vector does for us is it's going to change the magnitude, but keep the direction. So this is where we start to get a little formula that we have to think through. So a vector u that has a length, u of 1. That's a unit vector. So when you do the distance formula, you get 1 back. That's a unit vector. So that's the name of it. If v is not the 0 vector, we're not going to use the 0 vector to try and get 1. It's not going to happen. Here's how we find it. That unit vector equals the vector divided by its magnitude. And it makes sense in a strange little way, because what we do is we take the vector and we divide it by its length. Of course we should get 1, because the vector divided by its length should give you 1. But most of the time we think of it like this when we're actually finding it. You know, we just put a 1 over the magnitude of the vector and then take that times the component form to make sure we get a unit vector. So this is a unit vector in the direction of v. So what this is going to do for us is it's going to keep the direction, but allow us to change magnitude. And that's what they want you to do in problems 39 and 40 in the homework. So when you get to those, don't overthink them. Just come back to this and say to yourself, okay, if I have the unit vector and I know what they want for magnitude, then I can just use it as a scalar and multiply. And things will be just fine. So away we go. Find a unit vector in the direction of v, and it is in component form from negative 3, 2, and then verify that it has a length of 1. Okay. Well, the formula is 1 over the magnitude of v times vector v in component form. So let's see here. Well, I would need to know what's the initial point for this. What is the initial point for that? 0, 0, exactly. So that makes this formula easier because remember the pieces they had up there were x of 2 minus x of 1. X of 1 is 0. We don't need that. So this is where they switched and said, let's call it A and B. Whoops. I'm in the wrong spot. And just do square root of A squared plus B squared. Go a little faster. So the square root of negative 3 squared plus 2 squared. 9 and 4. I'm supposed to take 1 over the square root of 13 times the vector negative 3, 2. And that's going to give me my unit vector. It will. It will. It's not going to be pretty, but it will. So negative 3 over the square root of 13 and 2 over the square root of 13. Now we're not going to rationalize it enough. We're going to use this to figure out that the length what's the initial point for this unit vector? 0, 0. All right. So that means we can just get away with our little square root of a squared plus b squared. We better get 1 or we did some math wrong. That's just how it works. So now we're going to verify the length of this vector is 1. Let's see. Square root of -3 over the square root of 13 squared plus 2 over the square root of 13 squared. We know the answer. First one to 1. We messed up. Let's see. Oh, well, there's no addition or subtraction in there, so we can distribute that 2. So that'll be 9 over 13. Same thing with the other set of parentheses. There's no addition or subtraction in there. We can distribute that 2. 4/13. What's 9/13 plus 4? There's our verify right there. So it works. Whenever these are in component form, the initial point is at 0, 0. So whenever we see that looks like a less than greater than symbol thing going on, that means the initial point is at 0, 0. All right, well, that wasn't too often. Let's see here. The two unit vectors I, 1, 0, and j, 0, 1, which I talked to you about before, those are standard unit vectors. Not real helpful for doing that. So, like I said, what we usually do is just change it into component form and have it be whatever numbers they have out front of it. So any vector v can be written as an expression in terms of standard unit vectors. So if we worked this backwards and we had AB and we wanted to have an I and j in there, we're never going to want to do that, by the way, for what we're doing for 6.1 and 6.2. We could do that. We could say, well, this would really be the scalar A times the standard vector 1, 0, and B times the standard vector 0, 1. And we absolutely could get AI plus B if we wanted to. But if I see this and I'm working on problems, I'm not using that. I'm using that. Much easier math, you know. So I just take those standard vectors out. It's explaining to me the horizontal and the vertical components, but that's what component form does. And that's the easiest thing to do the math with. So down here, here's the vector v at AB is expressed as a linear combination of two vectors AI and bj. So here is AI and bj, and there is that sum vector. Yeah, it is a parallelogram. It's a rectangle, which makes it a little nicer, but there it is. The scalars a and b are the horizontal and vertical components of the vector v. Now we get to the part where we need a little trick. Because what we want to do is start describing the direction. If the arrows are not there, if there's not a picture, we want people to know, hey, go this many degrees. That's where you need to get. Well, just like we learned when we were doing trig before on the unit circle, the x actually uses cosine to get us what we need. And then the y is going to be sine that gets us what we need. But we have this little magnitude piece in there because we're talking about vectors. So the magnitude of v times the cosine of theta, comma, magnitude of v, sine of theta, will actually give us that component. So, like I said, most of what we're going to do now is try to figure out how do you get people directions. You know, how do we do that? So the direction of a vector v is the direction angle, the angle theta, that v makes with the positive x-axis. So we want to start on that positive x-axis, describe to people, go this far, and you'll know where my vector is. Using trigonometry, we see that the horizontal component of v is the magnitude of v, cosine theta, and the vertical component is magnitude of v, sine of theta. Solving for those is called resolving a vector. So if they ask you to resolve a vector, what they're wanting us to do is figure out the components that would make this happen. And that's what we need to do next. But probably looking nervous by the way. All right, so resolving a vector. If v has direction theta, the components of v can be computed using that little baby formula right there. Magnitude of v, cosine of theta, comma, magnitude of v, sine of theta. From the formula above, it follows that the unit vector in the direction of v would just be cosine theta, sine of theta. It's like just factoring it out, you know. We say, well, both of these have a v, so can't I just take out that magnitude of v and think of it as a scalar? And absolutely you could. Parentheses versus the symbols. Get used to that again. Having these vectors since last year at this time. So what they want us to do is find the components of a vector. But before we do this, I need to remind you of something. And that is, when we grab our calculator, most of the stuff is going to be in degrees. So we're going to need to have degree mode. Secondly, we have to remember that when we use the calculator, let me find some space here. The calculator is going to give us answers in the PVR. You remember PVR? Principal value range. That's the doorknob. So sine, cosine, and tangent. So our calculator is going to give us answers for sine that are in first and fourth quadrant. It's going to give us answers for cosine in first and second quadrant. And then it's going to give us answers for tangent back in first and fourth quadrant. So sine, cosine, and tangent. So usually what I'll do is just use a picture, you know, and go back to, all right, here's where I know it is. This is what my calculator told me. How do I move that to the right quadrant? It says, find the components of vector v with direction angle 115 degrees and magnitude of 6, using no technology except to approximate the exact trigonometric solution. Well, take a look at it there. That doesn't look too bad. I mean, they gave us the formula, so let's use it. Magnitude of v, cosine theta, magnitude of v, sine theta. Magnitude. They gave us that. Wow, they're handing us stuff. 6 cosine of 115 degrees. And 6 sine of 115 degrees. Well, I'm not working backwards to find angles in this one, so I can just let the calculator tell me this. You know, I don't really need a picture. They gave me a picture. It's working. I can go with it. So, mode degrees 6 cosine of 115. Negative 2.536. 6 sine of 115. 5.438. But always take a second look at it and make sure that this makes sense. Look at where that vector is supposed to be at. Does it make sense that we would say the horizontal component is negative 2.536 and the vertical component is 5.438? It does. It should go left and up. That's what should happen. So we know things are working on our side. Remember, the PVR is when we're trying to find the angle. Here we already know the angle. But if we have to find it, then we have to think about PVR. And that brings us to this one. So with this one, it says we're going to find the magnitude and direction angle of each vector. So, let's see what we can do. Vector 3, 2 over there. Oh, that's in first quadrant. I always like first quadrant. Everything's all positive and good in there. All right. So magnitude, where's its initial point? 0, 0. Yeah. So you can just go ahead and use that little square root of a squared plus b squared to get magnitude of u. So square root of 3 squared plus 2 squared. Don't necessarily like using the same numbers again that we had earlier. It's a little bit different. Now, if I have to figure out what that direction is there, I'm not going to use any highfalutin formula. I'm going to come over here and drop down the right triangle and say, well, if the component forms here are 3 and 2, I'm going 3 to the right and 2 up, and that's opposite and adjacent. What's tangent? I'm just going to use that. So the tangent of equals opposite over adjacent, 2/3. It's in first quadrant. Tangent's PBR includes first quadrant. We should just be able to do the inverse tangent to this and have our angle. So inverse tangent of 2/3 in degrees. 33.690 degrees. Not what you'll see if you look in the book. In the book, they try to make this, well, they want you to use the fact that if you take the magnitude times the cosine of theta, you should be able to get that component form there, which in this case would be a 3 for the x value. But it's overdoing it for what we're going to need in these two sections. So now, -2, -5. I already noticed the problem. Where's -2, -5? Quadrant 3. Tangent's PBR in quadrant 3. So we're going to have to do a little thinking about that when we get there. But let's worry about that when we get to that. Alrighty, so far we need magnitude. Oh, this one's B. Can we use a nice little short formula? How do you know? Yeah, it's component form, so initial point's at 0, 0. So square root of -2 squared plus -5 squared. Square root up? Yeah, that's not beautiful either. The good news is we don't have to do anything with it, so square root of 29. Like I said, the book has you use that to go through other stuff. We're not going to do that. Here's what we're going to do. We're going to draw them, and we're going to use right triangle trig to figure out how to tell somebody where that angle is. Because the component form gives me, hey, this is a -2 and this is a -5. And every time here, I'm going to be able to use tangent to figure out what that angle is. So I need the tangent. And I can't use beta because they already used that. I'll just make it theta here. Tangent of theta. And then I can just see where it's at, and I can do some adding to figure out what the angle is. So opposite over adjacent is going to be -5 over -2, which is just a positive 5/2. So we need the inverse tangent of 5/2. And then we're going to do a little figure and get it in the right block. So let's see here. Inverse tangent, 5 divided by 2. 68.199 degrees. All right, so my little angle theta here is 68.199 degrees. But I'm going to have to do something to that to get people to that position because we start on the positive x-axis. So I think, all I really have to do is get them here and then tell them to add 68.199. How many degrees is here? 180. That's all we have to do. We don't need to make this any more difficult than that. And that way I don't have to worry so much about PBR if I just use the visual. So 248.199 degrees. So with the visual, like I said, you don't have to worry quite so much about PBR. And as we've told you before, your last step should be calculated. You know, everything else up to that should be a perfect answer, and then calculator at the end. All right. I had high hopes of getting as far, so that's good. Monday, seniors, we're going to go through those 4-word problems. So I will make sure that I record that. You're not getting as much educational value for your buck in Chapter 6, because these homework assignments go really fast. I know you'll all be disturbed by that, but don't think you're doing something wrong, because you're not. You know, vectors are supposed to be very basic quantities when we first start to learn about them.